Today we shall discuss some numericals and chemical kinetics, right? So we shall discuss about numericals here, right? So before getting into that, we shall cover the important points, the important topics in chemical kinetics from which the questions may be, right? First and foremost, important part is rate of the chemical reaction, right? Rate of the chemical reaction. That's the most important point. What is rate actually? Rate is nothing but change in concentration, right? Change in concentration. Let us denote the concentration by here with respect to time. Change in concentration with respect to time. That is called the rate of the reaction. And its unit is, the unit of rate of the reaction is mole per liter per second. Mole per liter per second. And in the case of gaseous substances, it will be atmosphere per second, right? Atmosphere per second. Got it? And this rate will be classified into two types. That is average rate and instantaneous rate. Average rate and instantaneous rate. Right? Instantaneous rate in the sense at particular time. At particular time. And average rate means within two time period. Within a time period, T1 and T2. Within the gap T1 and T2, what is the rate of the reaction? That is the average rate reaction. This is a particular rate reaction. That is instantaneous rate of the reaction. Okay. And factors affecting the rate. Next, factors affecting rate of the reaction. Factors affecting rate of the reaction. What are the factors we can list out? You can have this group CTC, SC. So if you remember this code, it will be easy for us to understand the factors affecting the rate of the reaction. What is CTC? C is concentration, C is temperature, and this C is catalyst, and this is surface area, and this is activation energy. That is concentration, temperature, catalyst, surface area, and activation energy. Right? These are the things which influences the rate of the reaction, right? Which influences the rate of the reaction. Okay, and then rate law. Rate law. And what is rate law actually? For equation, let us consider this equation. A of A plus B of B gives C of C plus D of D, right? If you have to write the rate of this reaction, it can be written as R is equal to K into concentration of A raised to its power, that is A. This A may or may not be equal to its coefficient, right? Concentration of B raised to its power. This B may or may not be equal to this B, right? So this can be written as minus of dr by dt, right? Minus of dr by dt, okay? That's it. This is the rate law. And questions will be there in order and molecularity of reaction. So shall I rub all those things? Shall we go for the next thing? Right. Next point is order and molecularity. Order, molecularity. Order and molecularity of the reaction. Right. What is the order of the reaction? Sum of powers of concentration. Sum of powers of concentration terms in rate law. rate law, right? So for this equation, A of A plus B of B gives C of C plus D of D. So the rate we had written as rate that is equal to rate constant into concentration of A to the power of A, concentration of B to the power of B. So here what is the order of this reaction? Sum of the powers of the concentration terms in the rate law. That is order is equal to A plus B here, right? So this is the order of the reaction. Got it? And what is molecularity of a reaction? What is molecularity? The molecularity is number of reacting species. Number of reacting species. Number of reacting species in elementary step. In elementary step. Right? This is a molecularity of the reaction. So this is what this is also most important. Then the important topic is collision theory. Collision theory. Right? And then Arrhenius equation. Arrhenius equation, as you know, K is equal to A to the power of K is equal to A into E to the power of minus EA by RT. So this is Arrhenius equation, and this can be written as log of K is equal to log of A minus EA by 2.3303 RT, right? And this also can be written as log of K2 by K1, that is equal to EA by 2.303 RT T2 minus T1 by T1 T2. So these are the equations we have to use in the Arrhenius theory, right? Okay. Based on the situation, we have to use this equation. Got it? And then we have to think about integrated rate equation. So what is Arrhenius equation? What is activation energy here? EA. Activation energy, EA is known as activation energy. Activation energy. What is this activation energy? That is minimum energy. Minimum energy required by the reactants to form activated complex. To form activated complex. To form activated complex. So this is the activation energy. Got it? So this can be written as EA is equal to threshold energy. Threshold energy minus average kinetic energy. Average kinetic energy of reacting molecules. Average kinetic energy of reacting molecules. Right? So this is also most important. And the important topic in kinetics is integrated rate equation. Integrated rate equation. Integrated rate equation. And In the order of the reaction, we have to first order, second order, and the pseudo first order is also most important. Pseudo first order reaction. Pseudo first order. Pseudo first order reaction. It means that, what does it mean that one reactant in excess. One reactant in excess. One reactant in excess. So examples, acid hydrolysis, of ester. And next example is inversion of sugar. Inversion of sugar. Right? So these are the main topics. And another important topic is we have to remember, that is half-life period. Half-life period. Right? That is T half. So T half for first order reaction is, we have to remove this one, 0.693 by K for first order reaction. For zero order reaction, it is concentration of R naught by 2K. So this is for zero order reaction. Got it? I think this is enough. Then we can get into the numericals now. Let's work out this question. For a reaction, reactant gives products. The concentration of the reactant changes from 0.03 to 0.02 in 25 minutes. Calculate the average rate of reaction using units of time, both in minutes and seconds. Right? This is the question. So let us work it out. So what is given here? That is, the reactant gets converted into products. So what is the time period given here? The concentration changes from the concentration R1. Let us take it as, this is R1. The concentration, initial concentration, that is equal to 0.03 m, and R2. The concentration, next concentration is taken as 0.02 m. And what is the time period? 25 minutes. That is, the difference in time is 25 minutes. Right? So what they are asking for? Average rate of reactions. So average rate. What is average rate? Average rate of reaction. That is nothing but, what is average rate of reaction? That is del R by del T. Del T they had given, del R we have to find out. So del R is nothing but, we will find out del R. So average rate, that is equal to del R, that is nothing but R2 minus R1, right? Concentration at the final and initial, R2 minus R1 by del T, we can substitute as 25 minutes. Del T we can directly substitute as 25 minutes, okay? So here this can be written as 0.02 minus 0.03 by 25. So that is equal to minus 0.01 by 25. So that is, the thing is 4 into 10 to the power of minus 4. 10 to the power of minus 4 mole per liter per minute. Right? Mole per liter per minute. But they're asking for minutes as well as in seconds. So we have to convert this into seconds. So this can be, what is it? 4 into 10 to the power of minus 4. For seconds, we have to divide by 60, right? 60 mole per liter per second. Mole per liter per second. Mole per liter per second. So that will be, that is equal to 6.6 66 into 10 to the power of minus 6 mole per liter per second, right? Mole per liter per second. So this is the answer for seconds and this is the answer for minutes, right? And this is the answer for minutes, okay? For a reaction 2A plus B gives A to B, given the rate. Calculate the initial rate of the reaction when the concentration of A is 0.1 mole per liter and the concentration of B is 0.2 mole per liter, and calculate the rate of the reaction after A is reduced to 0.06 mole per liter, right? First A value is 0.01 mole per liter and in the second part the A value is 0.06 mole per liter. For calculating the rate of the reaction, we require the concentration of B2, right? So when A is reduced to 0.06, from this we have to calculate the concentration of B. Okay. So let us work out the first part of the reaction. Calculate the initial rate of the reaction. Let us write down. So they had given itself, that is rate that is equal to rate constant into concentration of A, concentration of B raised to the power, right? So the concentration of A they had given is, the concentration of A they had given is 0.1 mole per liter, 0.1 mole per liter, and concentration of B is 0.2 mole per liter, right? And let us substitute in this equation K value they had given, that is equal to 2.0 10 to the power 6. So let us substitute in this equation 2.0, that is 2 into 10 to the power of minus 6 into concentration of A 0.1 into concentration of B 0.2 square, right? So this can be written as 8 into 10 to the power of minus 9 mole per liter second square, right? Per second square, right? So this is the answer for the first part, right? Up to this. Now calculate the rate of the reaction after A is reduced to 0.06 mole. Let us write the rate equation here. So the rate equation for this reaction, is rate of concentration of A with respect to time dt, that is equal to difference in concentration of B with respect to time. These two are reactants, so we have a minus charge. So this is product, concentration of A to B, right, with respect to time. This is a rate equation as we know, right? So what is the thing given? The concentration of A initial. The concentration of A initial is, so what is the concentration here? 0.01. That is 0.1. The concentration is 0.1. And the concentration of final, that is the concentration of A final, what has been given as 0.06 m. That is equal to 0.06 m. Got it? So the amount of A reacted we can calculate it from here. The amount of A reacted, so that can be calculated from initial minus final, 0.1 minus 0.06, that is equal to 0.04 m. So that is equal to 0.04 m. Let us work out the concentration of B. We have to find out from here. Concentration of A we got it, so we have to find out the concentration of B. Let us write the equation. Concentration of B with respect to time, that is equal to concentration of A with respect to time, right? Concentration of A in the sense 2A. Here it is 2A, so it should be written as 1 by 2. So it should be written as 1 by 2. The minus and the minus get cancelled. So we can substitute here the thing. So this can be written as 1 by 2. What is the concentration of A we found out? Into 0.04, which is equal to 0.02 molar. 0.02 molar. What is it? That is, concentration of B has been found out as 0.02 molar per second. The concentration of B has been found out as 0.02 molar per second. So the initial concentration of B is 0.2 mole, right? The thing reacted with A is 0.02 molar. So let us get the final concentration of B. Let me work out it here. That is the concentration of B initial. So that is what they had given here, 0.02. That is 0.02 m. The concentration of B reacted, what we found, 0.2 m. Yeah, here. So we can calculate the B final. B final that can be calculated from 0.2 minus 0.02. So that is equal to 0.18 molar. 0.18 molar. Right? So we got the B final here. So let us substitute the B final in the rate equation. Right? So when A is reduced to 0.6, let us substitute in this equation. That is rate is equal to rate constant. What is rate constant? 2.0 into 10 to the power of 6 into what is A here? 0.06 into 0.18 square. 0.18. Let us change the color to make the difference here. Okay, 0.18 square, right? So this can be written as 3.89 into 10 to the power of minus 9 mole per liter. Mole per liter. So this is the final answer. So let us have a check over here. Is what is that? Calculate the initial rate of the reaction when A is equal to 0.1 mole per liter, B is equal to 0.2 mole per liter. This is a direct question. So they had given the rate equation. So simply we get substituted and we can find it out. Right? This is the answer for the first part. So this is our code for the first part. And second part, what they had given, calculate the rate of the reaction after A is reduced to 0.06 mole. So A is reduced to 0.06 mole means A initial has been given as 0.1 now, and A final has been given as 0.06. So from this we are finding out the A reactor. So we got the A reactor here. From the A reactor, we are finding out the B value. B reactor, right? From this, we are finding out the B reactor. From the B reactor, we are finding out the B final. So by substituting the B final in the equation, we are getting the final value 3.89.